Alright, so this is where I was in the last video. I know I keep saying that, I'm sorry. It's just, it's for continuity purposes. Alright, so, so this, I think I pretty much covered this. We start to see this pattern. Let's take a look. Alright, so you keep doing this, by the way, with more and more stars, and you get the full HR diagram, which we're going to get to. Before that, let's discuss what's called, remember, so before we do this, just as a reminder, we discussed finding the distance to stars, right? So we use parallax, the parallax using the Earth's orbit around the sun as a baseline. Just to let you know, there was a spacecraft that extended the baseline. It was called Hipparchus, right after the guy who, 2,000 years ago came up with the magnitude scale, the apparent magnitude scale. So there was an actual spacecraft. I think it was in the 1990s. Just to let you know, there has been another. And so what did the spacecraft Hipparchus do? It extended the baseline out. It extended further than the orbit of the Earth. So it allowed us to measure using a parallax, a stellar parallax, allowed us to measure that to stars further than about 200 parsecs. In fact, there has been another spacecraft that the European Space Agency launched a few years ago. Actually, I think it was in the 2016. I'm thinking I might be off on that exact date. The spacecraft is called Gaia. And Gaia has actually extended our ability to measure the parallax. So not this thing called stellar. So a stellar parallax. Okay, not this thing that we're about to talk about. Out to about 10,000 parsecs. So that's a good fraction of our galaxy, right? I mean, it's almost 1/3 of the diameter of our galaxy. All right. So what about stars that are further than even Gaia can measure? And of course, Gaia, we have not measured every single star within 10,000 parsecs. The method that we use to go beyond what Gaia's ability is, and also just using what people did for the last 100 years since before Gaia came along. Stars, let's say a typical star 1,000 parsecs away. How do we find the distance of that particular star? So we use this method called spectroscopic parallax, which, as it says right here, it's a really bad name. That's the first thing that you should know about it. It has nothing to do, as it says right here, with parallax, right? A better name would be, spectroscopic distance measurements. The reason they say parallax, of course, is because astronomers associate parallax with distance measurements, right? But again, it has nothing at all to do with parallax. You never, ever, remember, parallax, you're using a baseline, you're measuring the shift in a star's position. This has nothing to do with that at all. All right. This is actually using the HR diagram to come up with what the luminosity is, and then we'll figure out the temperature, and then from the spectral classification and this absolute luminosity scale, we can come up with what we think the luminosity is, or we estimate. All right. So here are the steps. All right. What's called the spectroscopic parallax. Again, a really bad name, but we're stuck with it, right? It's one of those things in any field astronomy is no different. Humans came up with these names, and they kind of stuck with us. There's all sorts of things. For example, there's one in physics that I always talk about with my physics students. There's a famous thing called Ohm's law, right? Ohm was a guy. Anyhow, Ohm's law has to do with electricity, and even Ohm himself, the guy who came up with Ohm's law, found exceptions to that. And so it's still called Ohm's law, but technically calling it a law is not correct because there's exceptions to it. So it's similar, at least in the idea is similar to this idea of spectroscopic parallax. It's just a really bad name. All right, so here's how it works. All right, so this is how to measure distances to stars. You measure the star's apparent magnitude. Of course, that's something that you look at. We actually can do this in a much more accurate. It's not done with the human eye anymore. Of course, there are CCD charge coupling devices that can measure this. They're actually it's the electronic version of the human eye. It actually works somewhat similar to the human eye. Anyhow. That's in modern astronomy. That's what you're using, the CCD. All right. Anyhow, and then we also figure out what the star's spectral class is. Remember that O, B, A, F, G, K, N, L, and T. Anyhow, you figure out what that is, and then what you do is once you figure out what the spectral class is, you can estimate what the luminosity is. All right. So let's look back at this. This is not a good example. Let me go back. I'm just going back a couple of slides here. Oh, I thought I had it. All right, I'm going back too far. Sorry. I thought they showed this as the lower part of the horizontal axis. They'll often just put the spectral classes down here, right? Anyhow, I mean they're showing it here, but they're also showing the temperatures. So from the spectral class, you can go up and you find the particular star that you're talking about on the by the way, it has to be a main sequence star. If it's not main sequence, there are other ways you can do this, but main sequence stars are the standard. So let's say you find a star. My cursor here. All right, so let's say you find a star like this. That is on the main sequence. So you go straight up, and that would be a K type star, and then you go. You find the star on the main sequence, and then find where it is on the luminosity, on the absolute luminosity scale, on the vertical axis. Okay, so if I went right here, my particular. So again, the K stars, they're numbered 0 through 9, so to get all the way to the M, and each of them are labeled like that. I think ours is like a G2 star or something like that. Anyhow, you find exactly where that star is, and that'll tell you what very precisely what the luminosity is on an absolute scale. So that's the part where you say you're estimating what the luminosity is. All right. So once you've estimated the luminosity, then you have the fact that the inverse square law can be applied, and you have the luminosity. You've measured the absolute magnitude. You can work out what the distance is. All right. So later, let's go back just a couple of slides, and this, right. So the luminosity, the temperature, and then R would be the distance from that star. All right. So you'd have to You take the square root, of course, of everything, but that's the general idea. All right, so that's ultimately how you'd find distance. And then, of course, you can compare this spectroscopic parallax to traditional parallax, right, with stars that are close enough that the traditional parallax works. All right, this spectroscopic parallax works well out into the universe, well out beyond our galaxy into other galaxies. Let's see, it goes, well, it goes, it doesn't, you can't do this with every star, like halfway across the universe or something like that, but it does work out, to huge distances. So for example, so this spectroscopic parallax will work out, accurately out to, let's see. I'm sorry, spectroscopic parallax looks like it'll only go out to about roughly 10,000 parsecs. So I was wrong about that. It doesn't get us outside of our own galaxy. Although I thought that somebody was working on it. Anyhow, according to this little model here, they're saying it just goes out to roughly 10,000 parsecs, which would keep it within our galaxy. All right, so this method, that's what we're using this for. And then there are other methods to go out beyond, beyond our galaxy. Of course, that's Cepheid variables. And we'll get into all these as time goes on. All right, and there's the Tully-Fisher method for galaxies themselves, estimating the distance to individual galaxies. All right, so this is our stepping stone. So within the solar system, you can actually use radar. You can bounce radar off the moon. You can bounce radar. Well, you can't bounce radar off the sun because that energy just gets absorbed. But there are using orbital information about the planets going around the sun. You can estimate what the distance is very accurately, actually. To the sun, and then you can do the same thing to the distance to Mars, things like that. So you can estimate what the distance is to Mars using what's called Kepler's laws, and then verify that using radar. Okay, so that's there are certain objects that you can do that with. When you get outside of the solar system, out to about 200 parsecs, which, as I mentioned, is now, because of the Gaia spacecraft, goes all the way out to 10,000 parsecs. You can use direct measurement of stellar parallax, right? Of course, Gaia has only been up up in space for, maybe half a dozen years or so. I forget exactly when it was launched, but, it certainly hasn't measured all the stars that are within 10,000 parsecs. So the general way to measure stars between 200 parsecs and 10,000 parsecs is using spectroscopic parallax. Again, has nothing to do with parallax. And then going beyond that, we're going to find we'll use what are called Cepheid variables, variable stars, basically. We'll get to that later. All right, so let's see. Spectroscopic parallax calculations can be misleading if the star is not on the main sequence. All right, so and I think I mentioned that. So if you want to be on the main sequence, any of these stars that are off the main sequence, like these, especially these giant stars, giant or even supergiant, you want to stay away from those. As far and there's a method of figuring out whether stars on the main sequence or not. We'll get into that again. So the big thing is the width of the spectral lines. From the width of the spectral lines, we can remember people have been looking at this stuff for 100 years, and so we know this pretty well now. We've been measuring these things for quite a while, and so you come across some new star. or not new star, of course, some star that nobody has looked at before.